A few weeks ago, we talked about how to partition matrices and vectors and how to then perform matrix vector multiplication with them. We now show how this extends to matrix-matrix multiplication. Rather than proving this rigorously, we build up intuition by looking at a sequence of examples and then state the result. Consider how to compute C equals A times B. Let's start by partitioning C and B vertically into two submatrices. Multiplying A times the partition matrix B is the same as multiplying A times each of the submatrices. If we look at how the 1, 2 element is computed by taking dot products of row 1 with column 2, we see how the 1, 0 element of submatrix C1 is computed by taking the dot product of row 1 of A with column 0 of B1. Here is how I remember how to perform this partitioned matrix-matrix multiplication. I start by remembering how to multiply a scalar, 3, times a row vector with two components. In the partitioned matrix-matrix multiplication, the scalar 3 is replaced by A and the components of the row vector by B0 and B1. You then mimic how you would scale the row vector with the symbols. The thing to keep in mind is that matrix multiplication does not commute, except in special cases. Let's do another example where C and A are partitioned horizontally. Again, track how the 1, 2 element of C is updated with dot products. Again, you can remember this by remembering how to multiply a column vector by a scalar. Each of the components is multiplied by that scalar. You mimic this with the symbols in the partitioned matrix-matrix multiplication. Again, in general, matrix-matrix multiplication does not commute. Here is another example where we partition A vertically and B horizontally. This time, this results in a dot product with submatrices. Focus on the 1, 2 element. It is computed as the dot product of row 1 of A with column 2 of B. But we remember that the dot product of partitioned vectors is just the sum of the dot products of the subvectors. But we remember that the dot product of partitioned vectors is just the sum of the dot products of the subvectors. Here is how we remember this one. Replace the symbols with scalars. Remember how to multiply. In this case, we compute a dot product. Mimic this with the symbols that represent the submatrices. Finally, we partition all three matrices into 2 by 2 blocked matrices. If you look at the presented result, you will see that we have just performed a matrix-matrix multiplication with 2 by 2 matrices. Again, track how the 1, 2 element is computed. It is computed as the dot product of row 1 of A with column 2 of B. But that row of A now spans 2 submatrices, and the column of B spans 2 submatrices. Carefully see how this translates to inner products with rows and columns of submatrices. Again, you can remember how to perform this block matrix-matrix multiplication by remembering how to multiply 2 by 2 matrices of scalars. Here's the general result. If you partition matrices C, A, and B conformally into submatrices, then the ij block of C is just computed as the dot product of the ith row of blocks of A with the jth column of blocks of B. Here we remind you how matrix-matrix multiplication with matrices of scalars is defined. If you go back and forth, the similarities should be self-obvious. To summarize, block matrix-matrix multiplication works the same way as matrix-matrix multiplication with scalars, except that the scalars are replaced by blocks, which we also call submatrices. The other thing to remember is that multiplication with these submatrices often does not commute.